Welcome back to Modern Physics. In this chapter 9, we're providing an introduction to atomic physics. This is going to be much more basic than you will cover next year in quantum mechanics, and we are skipping much of the painful mathematics. So we'll start with the very simple Bohr model to describe the observed emission lines in hydrogen. We'll see that this is surprisingly effective at describing some of the emission lines and energy states in hydrogen, but is not applicable for other emission lines and definitely not for other atoms. Then we'll move on to the results of applying the Schrödinger equation to the hydrogen atom, which you can do quite painfully analytically. And then this will show a quantization of angular momentum, and we'll see what that means. All right, starting out, we're looking at the observed bright peaks of light that you would see when you look at the spectrum from an excited hydrogen gas. And because these particular bright peaks in the spectrum were in a very narrow range, they're known as lines, and we see for hydrogen on the bottom graph that there are, in this wavelength range, there are 4 of these lines. And starting already in 1885, Johann Balmer came up with a formula that was not based on any physical arguments. It wasn't really a model. It just worked for the data. And so if we look at the 1 over the wavelength of an emission line, we set that equal to a constant, which became known as the Rydberg constant, because actually work done later by Johannes Rydberg came up with this value. And this is related to 1 over some integer value. We'll call this 1 over nf squared minus 1 over another integer squared. Call it ni. And for the Balmer series, which are the 4 lines shown below from hydrogen, we get that nf is a fixed value of 2, and ni for these 4 emission lines are either 3, 4, 5, or 6. And there were other emission lines that were observed from hydrogen where instead of nf equaling 2, it now equals 3, and that's known as the Paschen series. And there's also the bracket series where nf is equal to 4. So one of the major efforts at the turn of the century and leading up to 1913 was to describe on a more physical level how you would get the Balmer series, how you would get that formula. And Niels Bohr came up with a model that worked. It worked at least for describing that equation. And he had 3 postulates, so this is what the model is based on. One is that the electron is in a circular orbit, and the important thing is that the radius, the distance of this electron from the nucleus, is only at certain values that are discrete. You can't have a continuous range in the radius. The second is that these orbits also have discrete values for their angular momentum. And since we're just looking at this one particle in a circular orbit, the angular momentum L is pretty straightforward. It is, you'll remember this from classical mechanics, it's the linear momentum mv times r, this radial distance, when it's rotating about that center point, which is the nucleus. And then the condition that Bohr came up with is that we have the reduced Planck constant, h bar, and that's multiplied by n, where n is an integer that has either the values of 1, 2, 3, 4, and so on. Okay, we'll look a little bit at where this comes from, but for now, this is just a statement, and we'll actually see it is problematic, but it worked for Bohr's model. The third postulate is that the photons you're going to see are related to a transition in energy levels of the electron in this system in the hydrogen atom. So we have a change in energy is related to the initial energy, total energy of the system, minus EF, which was the final, and that's related to H nu, which is that energy of the photon that is given off. Notice that it's EI minus EF, which is, it's the negative of what you normally think of as a change in energy. Normally you think of EF minus EI, and we'll see where that negative comes from. But if we think about this in terms of an energy diagram, which we have on the bottom right, then this final is going, say, from a higher state, a higher energy, to a lower one. And this diagram right now looks very confusing, but it'll make sense later on. Okay, so I said that we'll try to understand where this angular momentum comes from. And if we're looking at the wave-particle duality and the de Broglie wavelength, de Broglie himself came up with a way to try to describe why we had this angular momentum, L is equal to n times h bar. So what he did was he thought about this wave function and the idea that if it is describing this electron in a circular orbit, then you need a boundary condition basically where at one fixed point this wave function is continuous. So if you just cut it somewhere, as shown in the diagram on the bottom left, then one side needs to connect with the other. Think about wrapping a one-dimensional band around and making a cut. And for that to be the case, we have this distance, the circumference around the circle, is L is equal to 2 pi r. So that's just the circumference of a circle. And then that, what we're saying, is that for this to be continuous, we need it to match up, which would happen if over this, if you unwrap this band, then you can describe one wavelength that would fit in the whole thing, or it could be several wavelengths as shown here, and we can start to count them. We have 1, 2, 3, 4. It looks like there'd be 4 wavelengths in there. And we could have 5 or 6 or 7, but it has to be an integer value n. We then look at what L is. L, capital L, being the angular momentum. And we said that's mvr. Now, we also have that the linear momentum is p equals mv. And we had that p is equal to h over lambda using the de Broglie relation. So what we're now seeing is that this is now, we can substitute m for the mv, and we have h over lambda, okay, times r. Now, we can then substitute in that from this equation here, that r is equal to n lambda over 2 pi, So this now becomes h over lambda times n lambda over 2 pi. The lambdas cancel, and you get, you also have the relationship for the reduced Planck constant, h bar equals h over 2 pi, so you can also use that, and you get n times h bar, okay? Which is exactly what Bohr postulated here in his second